Okay, last week we started the new chapter, which was network layer chapter. So we learned about virtual circuit as well as the datagram networks. And then one of the popular device that we use at this layer is the router. So we look at the main architecture of a router and what are the main blocks and main function in a typical router. After that, so we start to learn the IP protocol that we utilized in this layer, which is an internet protocol. So more specifically, we learned the datagram format and how to solve the addressing issue in IP version 4. And we then moved to the ICMP for the control and error messages. This is the protocol that is utilized for communication between a node as well as the network to get some reports as well as some error messages. And then finally, we learned the new version of IP, which is called IP version 6. And what are the motivation behind IP version 6? Why we move from IP version 4 to 6, and how do we handle the mixed IP version 4 as well as the IP version 6. Now, this week we are going to move to the core part actually, which is very important. So it's called routing algorithms. So how do we route a packet or datagram from source to destination? What are the main approaches in this case? And then we, in the first section, we will learn the main principle of these algorithms. And then in the second part, which is in the 4.6, we are gonna go over some of the specific protocol that we utilize in the internet, such as RIP, OSPF, and BGP. Okay, so first of all, there are two main approaches in terms of routing. The first one is called link state, the other is called distance vector, and there's some practical routing that we call hierarchical routing. So what is the routing and forwarding? If you guys remember, the routing is responsible to determine the end-to-end path from source to destination. And forwarding was responsible for determining how to direct datagram from one interface to another interface of router. So you can think of like an internal kind of router within a routing device. So we look at the header of a arrival packet that has a IP destination address, and based on this IP destination address, we look up the table, and based on the lookup table, we determine the specific output interface for that IP address, then direct this datagram to that interface. So in order to explain a routing problem, we use a graph theory. I don't know if you guys heard about graph theory. I guess so, because we teach this graph theory in the discrete math, and assuming that most of you guys took this course a while back ago. So let's refresh our mind about this graph theory. So we represent a network using the graph, and the graph consists of two parts. The first one is called node. This is the node U, node V, node X, node W, node Y, and node Z. And then we have the second part, which is called edge. Edge is the line that connects these the two nodes. Like this is an edge, and this is another edge, this is another edge that connects the nodes. In graph theory, we call it node and edge. But depending on the application, this node and edge can take different names. In the context of a network, this node is called routers, and the edge is called link. So we have the router device U, router device V, a router device X, and so on. And we have the link that connect these two routers. For instance, so we have the link of UV, UX, UW, YZ, and so on. So you can look at all the combination. So, and this graph abstraction is very useful to explain the, network basically. So in this graph theory, we have the cost function kind of, which we denote by CXX prime. So X is one of the node, X prime is another node. So we are trying to calculate the cost of link between X and X prime, and we'll represent with CXX prime. For instance, let's look at the cost of link between W node and Z node. This is the W node, this is the Z node. So based on given information, the CW as Z is equal to 5, right? In other words, the cost of link between W and Z is 5, or the cost between U and V is 2, and so on. So this cost can be calculated in practice based on different approach. It always could be one or inversely related to the bandwidth or inversely related to the congestion in the network. If you want to calculate cost of path, which is different than from cost of link, is that single cost of link, and path consists of multiple link. Let's say from X1 to XP in nodes. So you add them up, basically the cost of from X1 to X2 plus X2 plus X3 and up to XP minus 1 XP. So you add them up, all these link cost, and you obtain the final cost of path. So the question is here, I may have multiple paths from source to destination, or from one node to another node in this graph. So the question is, what is the least cost path between source to destination? In this case, let's say between U and Z. So this is the definition of routing. So algorithm that finds that least cost path is called routing algorithm. So routing algorithm is responsible to determine this least cost path that I explained. Okay, so we said that routing is responsible for finding the least cost path. The next question is, what are the approach in terms of routing? So we split into main two approaches. The first one is global approach. The second one is called decentralized approach. In global approach, all the routers have a complete topology and link cost information. So each router in the network has a complete topology and all the link cost information. So this approach is employed by the link state algorithms. The second approach, the router knows physically connected neighbors and link cost to the neighbors. So in this case, in contrast to the global approach, a router knows only physically connected neighbors and the link cost to neighbors. By iteratively processing of computation, they exchange this information with the neighbors. and then they can forward a packet or route a packet from a node to another node. And this approach is obtained, employed by the distance vector algorithms. So that's the main difference. In the first global approach, all the routers have complete topology and link cost information. In the second decentralized approach, a router knows only physically connected neighbors and the link cost to the neighbors. And this routing information can be static or dynamic in terms of, so what's the static routing? The routes change slowly over time. In the dynamic case, the paths can change more quickly. So that's why we need a periodic update, and sometimes we need to, the link cost can change because of the failure or other reason. So we need to quickly change and respond to this change. Okay, that was the main introduction, main principles of the algorithms. Now let's go to details of the first approach, which is link state approach. So there are many link state routing algorithm, and the most popular one is the DISCRA algorithm. So you may heard about this name. So network topology link cost known to all nodes. This is then, based on the global approach, as you know. And remember, from here is a link state algorithm, and this is one of the most popular algorithm for the link state. So in this case, all the routers, all the nodes in the network, they know the network topology as well as the link cost information. And this is achieved through the link state broadcast, and all the nodes in the network have the same information. So a node cannot have a different information from another one. So in these algorithms, we compute the least cost path from one node, which we call source, to all other nodes. And then it gives forwarding table for that node. And then we perform the iteration. After the k iterations, and know the least cost path to k destination. So I'm going to explain this algorithm before we start to explain this algorithm. So let me show you some notation that we're going to use. The first one is C of x and y, which is link cost from node x to y. And this link cost is equal to infinity if not direct neighbors. If a node is not at direct neighbors, we put the value of infinity for that cost. D of V, this is the current value of cost of path from source to destination. V is the current value. P of V is the predecessor node along path from source to V. Is the just one node before the current node, which we call predecessor node, along path from source to the destination or neighbor V. N prime is the set of nodes whose least cost path definitely known. So how this algorithm works, let's go over together. So first we have the initialization. This N prime set is first has a node of U, which is the source for all nodes V neighbors. All nodes V. If the V node is adjacent to U, then we assign a cost of UV to that current D of V. Otherwise, if it's not an adjacent, if it's not a neighbor, then we assign the value of infinity to that current value. And then we move to the iteration loop process in order to find W. that is not in n prime set such that d of w is a minimum. And then we add the w to the n prime, and then we need to update this d of v for all the v node that are adjacent to w and not in n prime set. So how do we update? We use this matrix, which is the minimum of d of v or dw plus cost of w and v. And we iterate this for all the nodes that are in n prime, and then we complete the algorithm. Let's give an example for that specific discrete algorithm. So assume that we have this network, which is shown by the graph, and we have how many, like 1, 2, 3, 4, 5, 6 nodes, and the link cost for each link is given. And then we are gonna find the shortest path from U to Z in this case. So according to the algorithm, the initial value for n prime is equal to U because these are source. And we have the d of v, which is the current value of the v node, and p of v is the predecessor node, and so on for the remaining nodes. So according to the algorithm, we need to assign the initial values when the source is equal to U node. So for the d of v, okay, the current value for d of v is equal to 7, as you see. So is the d of v, remember it was the current value of cost of path from source to destination v. So in this case, we evaluate the first node, which is v, and the d of v value is equal to 7. And then the next node is w, and the d of v value for is 3, and the predecessor node is u again, and the next node is x, and the d of x is equal to 5, link cost is equal to 5, and p of x, the predecessor node, is u. And because of y and z are not adjacent to the u, we put the value of infinity for both y and z nodes. So according to the algorithms, we need to calculate these minimum values. So which one is the minimum in this case? Of course, is the 3, 7, 3, and 5. So the minimum cost is equal to 3. That's why we select this path, so which is the W, and then we put this W here into the n prime set. Now we have UW. So the next, let's calculate for the V. So now we have 2 paths to the V. One of them is the previous, which has a 7, but now we have another new path through the W. So it's 3 plus 3 is equal to 6. So according to this matrix, the current value is 7 and the new one is 6. So that's why we select the minimum one, which is gonna be 6. And in order to reach to V through the W, the predecessor node is W. So we are already done with the W node, so we skip here, and now we have the X node. So still we can go through the W which is 3 plus 4 equal to 7, and the current value is 5. That's why we don't update. So because this is still minimum path between u and x, we keep this one. And then for the y, we can reach the only one is now, because it's through w, is 3 plus 8 is equal to 11, and the predecessor node we reach to the y through the w. That's why the predecessor node is w. Now we update this infinity to 11 comma w, and still we are not adjacent to the z. There's no any node that is adjacent to the z. So we are done in the second iteration. In this case, we have 6, 5, 11. Which one is minimum? Of course, this 5 is minimum. That's why we put the x into the n prime set to the path. Okay, uwx. And now the x is in on the path, so we can update, for instance, the v. Still the minimum is 6, so we don't update that. We are done with the w, and then we are done with the x. And in terms of y, we have x now, and we have a new path through the x to reach to the y, but the cost is 5 plus 7, which is equal to 12, which is greater than 11, so we don't update. We keep this 11 through the w to reach y. And now, because we added x, now x is adjacent to z, we are now ready to calculate the d of z. And d of z, because 5 plus 9 is 14, and the predecessor node is x. Okay, so we completed the d value for second and the third step. Now we have 6, 11, 14, and we select the minimum cost, which is v, right? So we add the v to the path, in other words, to the n prime set. Now we're left with two nodes. One of them is the y, the other is z. So far it was 11, because we added the v to the to the path. Now the y is adjacent to the v, right? That's why we have a new path, which is 3 plus 3, 6 plus 4 is 10, and it's less than the current value 11. That's why we update. And the predecessor value in this case is v to reach y. And we don't update the z because still y is not there. So, and we select the minimum among these two. Of course, it's going to be the 10, which is the value of y node. And then we add these to the path, the y node to the path. And then we left with z only, because we added the y to the shortest path. Now we can calculate alternative route through y to reach to z, right? It can be 3 plus 3, 6 plus 4, 10, and plus 2, 12, which is less than the current value. That's why we update the value of z to be 12, and the predecessor node is going to be y. And of course, this is the last one. Now we select this one, and we completed the discrete algorithm. So this then the next step is to construct the shortest path based on this table by tracing the predecessor nodes. So tracing predecessor tells us the first node is U. Then we move to the to okay, is 3. The source was U, that's why the predecessor was W. So we draw a line between U to W, and also we have a line between U and X, and then from W we have V and V W from U to W, and then V from V to Y, Y to Z. So we we trace the predecessor nodes to construct the shortest path, as you see. In such case, if you have ties which can be exist, then this can be broken arbitrarily by selecting one of them. This is how we construct the shortest path between source to destination node. Another example, second example. In this case, we have also 6. We have 6 nodes, and each node has a link cost shown on the graph, as you see. So our job again is to find the shortest path between U to Z. So we start with the U, of course, and we calculate the D of V and P of V values. So for the V, and the current value is 2, right? The cost and distance value. So D of V value is 2. And then for the W, we have a 5. For the X, we have a 1. And then for the Y and Z, because of they are not directly adjacent, so we assign the infinite value to dy as well as the dz. In the first step, of course, we select the minimum one. Which one is the minimum value? Of course, this is 1, which belongs to d of x. So that's why we put the x node to the n prime set. In other words, we add to the shortest path. And then in the second step, still the list cost is 2. We don't update this value for V. For the W, because we added X to the path, now we can reach to W through this 1 plus 3 equal to 4, which is less than the current value of DW. That's why we update to as 4, and the predecessor node is X. And we are done with the X. We are skipping the X. For the Y, to reach Y, yes, we can reach now because X is on the path and Y is adjacent to this X. And the least cost path is 1 plus 1 equal to 2. So that's why we update from infinity to value of 2. And the predecessor node to reach Y is X. And still Z is not adjacent any node on the path. So that's why we keep it as infinity. Okay, what's the minimum in this case? We have 2 candidates. One of them is V node, the other is Y. You can select any one of them. It's not a problem. So let's select the Y node. We add the Y node to the n prime set. Now we have, let's look at the value of V. Still the minimum one is 2, so we don't touch that value. And then the next one is D of W. So looks like we have a new path because we add the Y. Now the W is adjacent to the Y, and the alternative route is from 1 plus 1, 1 equal to 3, which is less than the previous value 4. That's why we update as 3. And the predecessor, of course, is going to be node Y. And then we are skipping X and Y, the Z now, because Y is on the path and Z is adjacent to the Y. Now we can calculate the D value for Z. So which is going to be 1 plus 1, 2 plus 2 equal to 4. That's why we calculate as 4, and the predecessor node is Y. So now we have 2, 3, 4. Which one is the minimum? Of course, these 2. So we add the node V to the n prime set. Now we are left with 2 nodes, which are W and the Z. So is there any update? No. This is 3, this is 4. Which one is the minimum? Of course, this is the minimum, 3. We select the W and then add this to the n prime set. And then we only left with the node Z. And then we add this Z to the n prime set, and we are done with all the nodes. Now, by tracing the predecessor node, we can construct the shortest path. You see from Y, Y, of course from Z to Y, and then Y to X, right? Which is here actually. Z to Y, we can reach to W, X, and U can reach to V through this. So this is how you end up with the shortest path, 3 from U to Z. And the resulting forwarding table in U, in U tables, only the node U has a such table. In order to, if the destination is V, you can reach through the UV link. Of course, if you want to reach to V, you need to follow the link of UV. If you want to reach to the X, you need to follow the UX. If you want to reach to Y, you need to go through X, UX again, UX, UX. So this is how it looks like a forwarding table that we constructed together. Any questions so far? Okay, let's look at some complexity of this Diskra algorithm. As you see, it has n nodes, and each iteration we need to check all the nodes W that are not in the n set. So that's why we need n times n plus 1 over 2 comparisons, and this is equal to O(n) square complexity. There are more efficient implementation possible of this algorithm, which has a complexity of n log n. Of course, there are some problem with this. The oscillations or the loops can happen. You see, the oscillation can happen. This is one of the problem related to the Diskra algorithm. So that was the link state algorithms. Now we are ready to move to the second approach, which was distance vector approach. So let's look at the distance vector algorithm. In this case, all the nodes doesn't necessarily have to keep the or know the network, the whole network topology as well as the link host. They just need to know their physically connected neighbors information, as well as the neighbor to destination information. So this is called distance vector algorithm, is based on the Bellman-Ford equation. So how do we assign a value? And so we utilize the dx of y is the cost of least cost path from x to y. And how do we calculate dx of y? We have the cost to the neighbors v plus from cost from neighbor v to the destination y. Because there are many, that can be multiple routes to reach from x to y using the middle node such as v in this case. So we need to calculate all of this and select the minimum taken over all neighbors v of x. So we calculate the all path cost to the neighbor, and let's say x has, v number of neighbor. So we calculate through all these neighbor and select the minimum one. Let's look at how it works. Give an example. So this is the cost of okay, first of all, let's give some distance vector like dv of z. That means from v to z is 5. How to calculate this? The minimum one is 2 plus 1 plus 2 is 5. From the dx of z is equal to 3. That means from x to z is 1 plus 2 is equal to 3. And dw of z, the distance vector between w and z is the minimum one. There are 5, this is not minimum one, there's 1 plus 2 through y, which is equal to 3. So this Bellman-Ford equation says, in order to calculate the the least cost path from u to z. So let's calculate together. There are how many neighbors? There are 3 neighbors of u, right? Is v, w, and x. So we need to calculate this matrix for all these 3 neighbors. Let's start with the first neighbor, which is v, and the cost of u of v is equal to 2 plus v2z. And the cost of the second neighbor is x, ux plus from x to z, the minimum distance vector. And the third neighbor is w, cost of uw plus the distance, the minimum distance vector from vw to z. Okay, let's put this value together. The cost of the first neighbor uv is 2 plus from v to z, which is given to be 5. So 2 plus 5. The second neighbor is x, and the cost of u of x is 1 plus the distance vector, minimum distance vector from x to z is 3. 1 to 2 through y, right? So it becomes 4. And the last neighbor of the u is w, and the cost of uw is 5 plus the minimum distance vector from w to z is 1 plus 2, 3. So 5 plus 3 becomes 8. So we have 3 values, 7, 4, 8. And we select the minimum path, which is the 1 plus 4. So this is the through the x, u to the x, x to the y, and z. So this is the shortest path that is going to be used in the forwarding table, u, x, y, and z. So some notes about distance vector algorithm. Dx of y, it shows the estimates of the least cost from node x to node y. And x, it maintains the distance vector dx, dxy, and for the y is element of n set. In this case, node x, the source in our case, knows the cost to each neighbor, v, is cxv. In our previous example, our source u knows three values: cost of u to the v neighbors, cost of u to the x neighbor, and cost of u to the w neighbors, which is we call cxv, and it maintains its neighbors distance vector that we just calculate, these dvz, dxz, dwz. So it maintains these distance vectors in the table, so which we call dv. And based on that, it add them up and it's find the minimum, the least cost path from source to destination. From time to time, each node sends its own distance vector estimates to neighbors. So because the change can happen on this distance vector, so that's why each node sends its own distance vector to his neighbors. So when the X receives new distance vector estimates from neighbor, it updates its own dv using the BF equation based on this one for each node of y. So how do we do that? We can do iteratively in a synchronous manner or in a distributed manner. So let's look at the first approach, each local iteration caused. So this local iteration is caused because local link cost change can happen, or dv update message from neighbor. In distributed manner, we have each node notifies neighbors only when its dv changes. Neighbors then notify their neighbors if necessary. So how this algorithm works? So you wait for the change in the local link or cost or the message from the neighbor. If there's such update, you need to recompute estimates. And if distance vector to any destination has changed, you need to notify your neighbors. Okay, let's give a specific example how this distance vector algorithm works and how this information is shared. Assume that we have three nodes, x, y, and z, and these are the link cost 217. And let's look at the node x table first, routing table. This is from xyz to cost xyz. So in the x node, from x to x, of course, is 0. From x to y is 2. And from x to z is 7, right? And because this from y to y and y to x is belong to the other table, so initially we don't have such values. That's why we assign the infinity value to these elements in the table, entries in the tables. So for the node y table, from y to x is 2, from y to y is 0, of course, from y to z link is 1, so 2, 0, 1, and the remaining are assigned to be infinity. And let's look at the node z table. From z to x is 7, from z to y is 1, and from z to z is 0. So these are the initial values in the tables, but we need to compute the remaining infinity values, right? The entries that has an infinity value. So this X is gonna share this table with neighbors Y and Z, and then Y is gonna share with X and Z is gonna share with X and Y. Okay, so let's say the Y and Z share their table information with the X node. Now we need to calculate, so because the new entries come to 01710, so we need to calculate the new entries for the X line. So from the X to Y, sorry, we need to calculate this distance vector and this dxy estimate, sorry, and the X estimate was, minimum of the Cx of Y plus dy of Y. So there are two neighbors basically for the X. One of them is the Y, the other is Z. For the Y, the cost is 2 and Y to Y is 0, 2 plus 0. And for the X of Z, so to reach the Y, we have two ways to reach from X to Y, right? One of them is the direct path, which is this, and the other is through the Z. And this is equal to 7 plus 1. So which is 2, 8. Which one is the minimum? Of course, 2 is the minimum. So that's why I put here 2 values. From X to Z, how to reach to X to Z? There are two ways. The first one is the direct. The other way is through Y to reach to Z, right? And let's calculate the dx of Z based on this matrix again. So it's 2 plus 1 through the Y and 7 plus 0. Now we have 3, 7. Which one is minimum? Of course, the 3. The direct one is more costly. That's why the minimum, the least cost path is through Y. So that's why it's going to be 3. So we update the value of X line in the X table. Similarly, you calculate, so you shared and you come up with this table for the Y and table for Z, right? For instance, for the Z, we have a change, but for the Y, we don't have change. From Z to X, for instance, Z to X is the minimum one is 3. That's why we put 3. From Z to Y is 1. And from Z to Z, of course, is 0. And then for the next time, we share among these tables and we keep update this if there's any kind of link change or any kind of failure or messages about the changes. Of course, there's some problems, issues related to this algorithm as well. If the link cost changes, so if the link cost change, for instance, we have 3 nodes for 150. Initially it was 4. Let's say the link cost changed to be 1. It reduced from 4 to 1. So the node detects this local link cost change, and it's going to update the routing information and recalculates distance vector. If distance vector changes, we need to notify neighbors. So let's say at T0, the Y is going to detect this link cost change, and it's going to update its DV metric, and then informs its neighbors, which are Z and X. Let's say the Z at T1 time, Z receives the update from Y, and it's going to update its table, and it computes new list cost to X, because the list cost was through the Y. 1 plus 4, it was equal to 5, and it's going to look at whether this change is going to affect its list cost to the X. It computes new list cost to the X and sends its neighbors its DV information. At T2 time, Y receives the Z update, and it updates its distance table. Y's list costs do not change because, as you see, so Y doesn't send a message to Z. Let's say now this 4 increased to 6, the link change. Of course, the node is gonna detect this local link cost change. And then we have a count to infinity problem in this case. And one of the solutions is poisoned reverse. Okay, let's compare both link state as well as the distance vector algorithms in terms of complexity, performance, convergence rate, and so on. So let's start with the message complexity. In the link state approaches, we have n nodes and e number of links. So and the complexity is going to be O of n times e, number of message will send. So in the DV, it's really hard to calculate this complexity because it depends on the number of neighbors and so on. So exchange between neighbors only, and the conversion time varies depending on the topology, of course. Speed of convergence and how fast it's going to converge in the link state is the O(n) square algorithm requires O(n) e messages, and this may have an oscillation problem that we show. And so in the DV is again convergence time varies because of there might be some routing loops and some another problem such as count to infinity problem. Let's look at the robustness of these algorithms. What happens if the router malfunctions? Assume that router start to malfunction, provide a wrong information or error, so the incorrect information. In case of link state, so each node computes only its own table. That's why there's no dependency. That's why that this error do not propagate over the network. But in case of distance vector, DV node can advertise incorrect path cost because this information is utilized by other nodes, so the error propagate through the networks. Hierarchical routing. So any questions so far? No? Okay, let's continue. Now the next topic is hierarchical routing. Okay, these are of course theoretical information or background about the routing algorithms in terms of link state and distance vector methods. But in practice, our routing studies does so far, we assume perfect case, ideal case. We assume that all the routers in the network are identical. And network is all consists of the all same routers, but this is not true in practice. So this organization can utilize that brand name of router, the other can use another router, so they're not identical. Of course, they follow up some standards, but all the routers in the networks may not be identical in practice. So what we're going to do in this case to handle this issue, think about you have a 600 million destination, and you cannot, put this in a table. Even if you put in this a table, you cannot, update the 600 million destination in a table. You cannot store all this destination in routing tables and exchange, all this information, and you're gonna, swap the links basically. And also, internet, we said that is a network of networks, and each network admin, of course, they may want to control routing within their own network. So that's why we need to come up with an hierarchical architecture in terms of routing. So we aggregate the routers into regions. So we put them together, these routers into regions, which we call autonomous systems. We call these regions as AS, autonomous systems. So routers in the same AS run same routing protocol, but we have an intra-AS routing protocol as well. So routers in different AS can run different intra-AS routing protocol. And then we have a gateway router at the edge of its own AS and has a link to router in another AS. Let's look at this interconnected autonomous systems. ASs. Let's say we have 3 AS, in this case AS1, AS2, and AS3, and we put them together, some router in each region. Like AS1 has a 1A, 1B, 1C, 1D, 4 routers. On the other hand, AS2 has 3 routers, 2A, 2C, 2B, and AS3 has 3 routers, 3A, 3B, 3C. So we have the forwarding table that is configured by both intra AS and inter-AS routing algorithm. The intra-AS, they set the entries for internal destination. Inter-AS and intra-AS routings, they set entries for external destinations. Let's look at the inter-AS task. So in this inter-AS task, we have again 3 AS, AS1, AS2, AS3, and assume that router in AS1 receives datagram destined outside of AS1. So assume a router, let's say 1D, receive a datagram that need to forward this datagram to outside of AS1. So the router is gonna should forward packet to the gateway router, but which one? We have AS2 and AS3 different gateway router. So in this case, AS1 must learn which destinations are reachable through AS2 and which through AS3, of course. And also propagate this reachability information to all routers in AS1. So it's going to obtain this AS2, AS3 reachability information, and it's going to broadcast among the routers within the AS1. And this is the job of inter-AS routing. So how to set up a forwarding table in router 1D. So in AS1, we have a router 1D, and how we're going to set up forwarding table in this router. Suppose AS1 learns that subnet X, this is the subnet X, is reachable via AS3. Of course, is connection. There's a connection link, as you see, is reachable via AS3 gateway 1C, for instance, but not via AS2. There's no any connection between subnet X and the AS2. An inter-AS protocol propagates reachability information to all internal routers. So it's going to propagate this information to all internal routers. And router 1D determines from intra-AS routing information that its interface 1 is on the least cost path to the 1C. And they're going to install the forwarding table entry as X, L. And then let's give an example in terms of choosing among multiple autonomous systems. Now, suppose autonomous system AS1 learns from inter-AS protocol that subnet X is reachable from AS3 as well as AS2 now. Previously, it was only from AS3, remember guys? Now we add the AS2 link as well. So to configure the forwarding table, router 1D must determine which gateway should be forward packets for destination X. This is also job of inter-AS routing protocol. So now suppose AS1 learns from inter-AS protocol that subnet is reachable from AS3 as well as the AS2. So, and the answer for that is called hot potato routing. So you send the packets towards closest of two routers. You learn from inter-AS protocol that subnet X is reachable via multiple gateways. Then you use routing information from intra-AS protocol to determine cost of least cost path to each of the gateways. And according to the hot potato routing, you choose the gateway that has the smallest least cost. After this selection, you determine from forwarding table that the interface 1 that leads to the least cost gateway, and you enter this X1 in the forwarding table. That's the summary of this example. Okay, this is the hierarchical case when it comes to the practice. Any question so far before going to the break? Okay. 15 minutes break, guys. Okay.